Good evening, everyone. I am Trevor Watkins. I'm the chair of the NEOACM, and I want to welcome you to our remote tech talk entitled Mobile App for Mars by our speaker, NASA software developer, Kurt Leucht. This tech talk is sponsored by the NEOACM, which stands for the Northeast Ohio Association for Computing and Machinery, and is co-sponsored by the teaching and learning team at George Mason University Libraries. NEOACM is a professional chapter of the International ACM, the world's largest educational and scientific profession. NEOACM is based in Youngstown, Ohio, and for over the last 10 years of our existence, we meet regularly to discuss diverse topics and function as an intellectual and geographical node of activity for the ACM members, the computing community, and the general public by offering seminars, lectures, forums, and the opportunity to meet peers and experts from many disciplines. Our speaker, Kurt Leucht, started at NASA's Kennedy Space Center 31 years ago as a young college intern and then graduated to electronics failure analysis investigator. He worked as a software developer and tester for several command and control systems and advisory systems. He discovered his passion while working on the NASA SwampWorks lab on software for robots and other systems that could someday help us live off the land on Mars during manned exploration missions. Now he performs exploration research and technology development. Mr. Leucht enjoys speaking regularly to all ages and abilities, from grade school students to colleges and professionals on such topics as robotic exploration of the moon and Mars, NASA's plan to send humans missions to the moon and then to Mars, swarming robotics and biologically inspired robots, NASA's KSC SwampWorks lab projects and capabilities, and NASA's intern program. Today, Kurt will speak on the similarities and the major differences between typical business software and software that is designed for the NASA Mars rovers. If you have any questions, as I mentioned before, please type them in the Q&A and they will, or in the chat, and they will be read by Tracy Hughes, which is our secretary. She will facilitate that after Kurt's presentation. So thank you, Kurt. Take it away.
Now, hopefully everybody can hear me without any weird echoes, and hopefully everybody can see my screen. If there are any technical issues with my audio or my screen sharing, you'll have to audibly come in and notify me, because while I'm sharing my screen, I can no longer see the chat. So let's get started. As Trevor mentioned, my name is Kurt Leucht, and I develop software for NASA at the Kennedy Space Center in Florida. And what I'm going to talk to you today about is writing apps for Mars. All right, mobile app developers and other software developers generally take great pride in their final products. They often brag about the features of their product. They might talk about its simplicity and its ease of use, or how it was designed with the end user in mind. Or they might brag about how efficient it is, or all the different platforms that the app runs on, or how well it performs, or how their app works even when offline, or how supportable or upgradable it is. In their detailed spec sheet, or maybe in their README files, they might even talk about what language their app was written in. Or they might discuss the process that the development team used and how the software was thoroughly tested, if their customers are focused on quality or certifications. Pardon me while I stop my camera. No sense wasting the bandwidth on my camera. All right, hopefully everybody can still hear me and still see my screen. And so all of these different features and specs can help an app stand out above the rest in the app marketplace. But how does a typical mobile app or business app compare to, let's say, the onboard software for a Mars rover? Well, this presentation is going to explore these features and these specs in an effort to understand the similarities and the major differences between common mobile software or business software and software that's designed specifically to run on board a NASA Mars rover. So buckle up, because this talk begins in 5, 4, 3. Okay, that's pretty cheesy. Let's just start. First, some background. Over the years, NASA has successfully landed and operated 5 mobile robots or rovers on Mars. Back in 1997, we sent Sojourner. That mission was planned and designed for only 7 days of surface operations, but Sojourner actually operated for 3 whole months. Then in 2004, we sent the twin rovers, Spirit and Opportunity. These rovers were designed to last only 3 months on the surface, but Spirit operated for more than 5 years, and then it got completely stuck in soft soil. But Spirit continued to operate as a stationary science platform for nearly a full year after it got stuck. And Opportunity, well, Opportunity actually operated for a full 14.5 years on the unforgiving Martian surface. Opportunity currently holds the off-world driving distance record of just over 45 kilometers, which is more than 28 miles. And if you want to watch a good documentary, go watch Good Night Oppie, which was released just a couple months ago on Amazon Prime. It's a very good documentary on the life and just how great Opportunity was. And so moving forward, in 2012, we sent the biggest yet, a car-sized Mars rover named Curiosity to Mars. And in 2021, we sent Curiosity's sibling, Perseverance, to Mars. Curiosity and Perseverance both had a design life of about 2 years. Perseverance has only been operating on the surface for a couple of years right now, but Curiosity has right now been operating for over 10 years, and it's still going strong. Curiosity was sent to explore a very special area of Mars called Gale Crater. Gale Crater is a very old and very deep Martian crater. This means that it has lots of exposed bedrock to study. Gale Crater is also very likely a dry lake bed, which is also very interesting for exploration. What's even more interesting than that is that Gale Crater actually has a mountain rising up out of the middle of it. It's 5.5 kilometers or 18,000 feet high. This mountain is commonly called Mount Sharp, but it's officially named Aeolus Mons. In Greek mythology, Aeolus was a floating island, and Mons is Latin for mountain. So Mount Sharp is basically a mythological floating island mountain, which I think is kind of cool. Curiosity has completed its thorough exploration of the Gale Crater Valley, and it is right at this very moment climbing up Mount Sharp. Perseverance was sent to explore a completely different, very special area of Mars called Jezero Crater. Jezero Crater is also a dry lake bed, but an ancient river appears to have emptied into this lake, creating a large fan-shaped river delta full of clay deposits, which is very exciting for geologists to study. The main bodies of Curiosity and Perseverance are basically the same, but the experiments and the payloads that are carried by these two rovers are quite different. While Curiosity was designed to analyze samples on board, Perseverance was designed to collect samples that will eventually be analyzed in detail by scientists here on Earth. A future Mars sample return mission is in the works, which is planned to pick up cached Perseverance samples, like the one shown in this picture, and fly those samples all the way back to Earth for study. Perseverance also had a stowaway of sorts on board when it landed on Mars. The Ingenuity Mars helicopter is a very successful Perseverance experiment or payload, which has made nearly 40 separate flights so far. The main scientific goals of both these big car-sized Mars rovers are to study whether Mars could have ever supported microbial life, to study the climate and the geology of Mars, and to study planetary habitability in preparation for future human exploration. By the way, I just love looking at photos from Mars, don't you? Now, Curiosity and Perseverance are pretty good-sized rovers. They're about the same size as a VW Bug. Their size and their weight are the reasons that we didn't just surround the rovers with large airbags and bounce them down to the surface like we did with our previous smaller rovers. This is obviously a computer animation, not actual video from Mars. So instead, Curiosity and Perseverance were both gently lowered down to the surface of Mars by a tether from a flying sky crane system. Also, due to their size and due to their power requirements, Curiosity and Perseverance are both powered by a radioisotope thermoelectric generator, rather than by solar panels, as were our previous smaller rovers. Radioisotope thermoelectric generators, or RTGs, that's fancy NASA speak for nuclear power. So Curiosity and Perseverance are both nuclear-powered rovers, which is pretty cool, don't you think? They are both designed with 6 wheels in what's called a rocker bogie suspension. Each wheel has cleats for traction, and each wheel is independently driven and independently controlled. And that allows these rovers to drive in soft sand and to climb over rocks. Each front and rear wheel can be independently steered, allowing these rovers to turn in place, as well as to execute wide arcing turns. High-resolution cameras on board both rovers are used to look for features of interest. If a particular surface is of interest to scientists back on Earth, like an interesting rock, for example, these rovers can actually vaporize a small portion of the surface with an infrared laser, and they can examine the resulting spectra signature to deduce the rock's elemental composition. If that signature is intriguing, these rovers can take a closer look using onboard microscopes and drills and other experiments and payloads. These rovers are equipped with 2 major communication systems. They have an onboard X-band radio that can communicate directly with Earth. They also have a UHF radio for communicating with any of the current NASA Mars orbiters. Talking to the Mars orbiters is the primary means of communication, since those orbiters have more transmit power and they have larger antennas for communicating with Earth than the rovers do. Curiosity and Perseverance have 2 identical onboard computers. One computer is configured as the backup and will take over in the event of problems with the main computer. These computers both run the VxWorks real-time operating system. It's a proprietary but deterministic operating system that's been proven to be reliable and secure, and it's widely used in embedded systems, both on Earth and in space. Onboard applications include apps for health monitoring and for system management. There are apps to handle communication with Earth and with the Mars orbiters, plus apps to handle entry, descent, and landing sequences, which all had to be completely automated. Then there are apps for situational awareness and location awareness, and mobility and navigation, most of which are at least partially automated. There are also apps that control and monitor the rover's arms and other mechanisms, plus apps to control and monitor all of the various science equipment on board. Okay, that was a very quick overview of our Mars rovers, with emphasis on Curiosity and Perseverance, our biggest and most capable rovers. So now let's do some basic comparisons between a typical mobile app or business app and the onboard software for a Mars rover. We'll start with simplicity and ease of use for the end user. Some of the most successful mobile apps today are very simple from the user's perspective. The more menus and buttons and data that appears on the screen, the more difficult it can be for the user to understand and navigate the app. Does everyone here remember Angry Birds? That seemed pretty silly to me when I first saw it. It's like, so you just pull back and let go? That's it? I don't think that's ever going to catch on. But boy, was I wrong. It turns out that users are really drawn to simple interfaces. Well, the primary users of the Curiosity and Perseverance rovers are the mission controllers or ground controllers, who are based at the Jet Propulsion Laboratory in Southern California. And the JPL, JPL is one of our 10 NASA field centers that are situated all around the country. The software that they use on their ground control workstations is actually quite complex. It has lots of data and lots of menus and lots of buttons. It also uses 3D virtual reality to fully immerse the ground controllers into the rover's actual environment. It is not exactly designed for newbies. But if we focus just on the onboard rover software, things get a lot simpler. The only interface to and from the onboard software are commands going to the rover from Earth and data coming back to Earth from the rover. Without revealing any sensitive design information, all communications to and from the rover follow the CCSDS specification. CCSDS stands for Consultative Committee for Space Data Systems. It's an international organization that creates standards for communicating with space assets like rockets and satellites and rovers. A lot of people think we just drive Curiosity and Perseverance around on Mars in near real time using virtual reality, but that's not quite how it works. It takes more than 10 minutes for radio signals to travel from Earth to Mars. And it takes another 10 minutes or more for signals to travel back to Earth. So real time and near real time joystick driving is just not practical, not at all. What we actually do is we plan an entire day's worth of rover activities or operations during the previous night shift. And then we upload those instructions to each rover at the beginning of its Martian day. You can think of it as sort of like a daily robot to-do list. Curiosity and Perseverance just start executing their to-do list every morning when they wake up, just like us humans. Coming up with this daily rover to-do list each night is no small task, though. It includes a large team of scientists and engineers. They study the images and the data from the previous day, and they hold meetings to decide what they want or what they need the rover to do the following day. Not only do they decide where the rover is going to move that day and the safest path that it will take to get there, but they also decide what images it will capture and what science instruments it will use and where it will use them. Once that planning work is all complete, it's time for the rover drivers. Yeah, that's what they're called. It's time for the rover drivers to write and test the actual rover command sequences. They use a custom scripting language for their command sequences, and they run these sequences in a 3D computer simulation to make sure they're correct. They use actual sensor data that was downlinked from the rover to fully experience the rover's world while they're writing and testing their command sequences. It's a pretty cool job, rover driver. The sequences that the rover drivers create get reviewed by a whole team of reviewers. It's important that we don't send any commands to the rover that could put the rover or the mission in danger. The rover drivers also have access to full-sized surrogate rovers here on Earth and an outdoor rock yard that they can use to test their command sequences. These rover drivers only get about a half a day to write that day's sequences, test them, and upload them to the rover. It's pretty intense work, but it's also quite rewarding. I mean, they're driving a rover around on Mars, for crying out loud. Now, the rover command sequences can be step-by-step detailed tasks like drive forward 5 meters, then turn right 30 degrees, then drive forward 4 meters, then activate Science Instrument A. Curiosity and Perseverance have hazard cameras and safety software on board that determine in real time whether or not the rover should stop executing its prescribed to-do list. And it might do that if it sees a steep incline or an obstacle or other unexpected issues. Rover command sequences can be more automated than that detailed step-by-step example, though. That is, if the ground team thinks that it's safe enough. They can send a sequence like this: enable auto navigation mode, then go to that rock over there. The auto navigation mode extends commanded drives into previously unseen terrain. It makes real-time decisions on board, similar to driverless cars here on Earth. Only Curiosity and Perseverance drive much, much slower than driverless cars here on Earth. During auto navigation operations, the onboard software uses the stereo cameras to evaluate roughly the next 1 meter's worth of terrain and obstacles. Then it calculates the safest route towards its destination, and it executes that route. And then it repeats that process until it reaches its destination. So it solves the navigation problem in small steps. I mentioned before that Curiosity and Perseverance drive much slower than driverless cars. Curiosity's top speed is just 0.09 miles per hour. Not 9 miles an hour, not 0.9 miles an hour, 0.09 miles an hour, less than 0.1, less than 1/10 of a mile an hour. That's 0.14 kilometers per hour if you prefer. And Perseverance's top speed is even slower due to Perseverance being a little heavier than Curiosity. Mars rovers are designed to drive slowly because it gives them a lot of torque. But Mars rovers don't really spend a lot of time driving at their top speeds. They actually spend a lot of their uptime studying rocks and dust and taking photos of the Martian landscape. In the 10.5 years that Curiosity has been carefully exploring the surface of Mars, it has only traveled about 18 miles, or about 29 kilometers. That's an average of less than 8 meters every Martian day, 8 meters per day. This robotic exploration mission is a very slow, very meticulous, and very detailed mission. So the ground controllers are not able to see constant feedback and constant data from the rover while it's executing its daily to-do list. The orbiting communications satellites only pass overhead a couple of times each Martian day, and each 8-minute pass overhead is only enough time for the rover to upload 60 megabytes of status and science data and photos. So the ground controllers are only able to receive information in discrete chunks a couple of times per day. So all that to say that the user interface for a Mars rover is basically just one guy or gal transmitting the day's to-do list from his or her control workstation in California and downloading the prior day's status and science data and photos. A lot of work goes on behind the scenes, and there are a lot of different verifications and checks along the way. But in the end, it's very similar to an old school FTP transaction, albeit to a very, very remote machine. Continuing our comparisons between a typical mobile app or business app and the onboard software for a Mars rover, let's move on to hardware and cross-platform topics. Mobile apps often run on several different platforms in order to be competitive in today's marketplace. The most common smartphones right now are manufactured by either Apple or Samsung or Google. The phone I like to carry is not the latest and greatest model. Those cost way too much for me. But the one that I carry is still fairly popular, and there are still a lot of this model out there in the wild right now. The phone that I carry has a 64-bit, 1.3 gigahertz dual-core processor. It has 1 gigabyte of memory and 16 gigabytes of storage. Reasonable specs for a modern cell phone, although albeit an older model. But sometimes, because I have an older phone, sometimes I push the limits on it, especially that 16 gigs of storage. It is surprisingly easy to fill that up with photos and videos. And so mobile app developers, they need to be aware of the limits of the hardware that their app is running on, and they need to design their app to work efficiently given those limits. If a mobile app developer hogs the CPU or hogs the memory or the storage to a degree that the user notices, that user is likely to just remove the offending app from their device. And thanks to social media, they'll probably tell all their friends to do the same. Curiosity's and Perseverance's onboard hardware platform was decided, it was decided years and years before the software team actually started designing and writing the onboard software. And so obviously that software only has to run on that single platform. Even in the lab during development, the onboard software was tested thoroughly on a copy of the same exact hardware that it would execute on board the actual flight rover. I mentioned earlier that Curiosity's and Perseverance's two onboard computers. Remember that these are identical computers and only one is actually used operationally. The other computer is reserved as a backup. These computers are limited in both speed and memory because they're specially designed to tolerate the vibration and the shock loads of launch and landing, plus the extreme radiation and large temperature changes found in space. Has anyone here ever had their smartphones turn itself off due to cold temperatures outside in the wintertime? I know I have. I mean, I live in Florida now, but I grew up in Illinois, and that has happened. Well, it's really, really cold on Mars. These rover flight computers use a legacy 15-year-old single-core 32-bit processor running at 133 megahertz. Does anybody in this meeting remember when desktop computers actually ran at 133 megahertz? It was a while ago. These rovers onboard computers, they actually run 10 times slower than my really, really old cell phone. And these rovers computers only have 256 megabytes of memory and 2 gigabytes of storage. So the computational resources on board Curiosity and Perseverance are fairly limited compared to the hardware that modern mobile app developers are used to working with. But I tend to run a lot of apps on my phone, and I imagine that's true for almost everyone. There's email, there's calendar, the alarm clock, the web browser, there's all the different social media apps, there's the camera, texting, games, music and video apps, GPS, not to mention the actual phone app. I occasionally do use mine as a phone. So how many apps really need to run onboard Curiosity and Perseverance? I mentioned earlier all the different functional categories of software. There's health monitoring, system management, communication, mobility, navigation. There's also mechanism control and science instrument control. This onboard rover software is highly multi-threaded. There are more than 120 different threads of execution all running simultaneously. So this onboard software is carefully designed and carefully reviewed by committee, not only to make sure that it's bug-free, but also to make sure that it is lean and mean. Wasted CPU and wasted memory are not tolerated on this project. The flight software onboard Curiosity right now, including the VxWorks operating system is only 21 megabytes in size. Think about that, 21 megabytes. That's for both the flight software and for the operating system. I mean, the alarm clock app on my phone is bigger than that. So it turns out that unlike many modern mobile apps, Mars rover software doesn't need to be flexible and run on more than one single platform, but it does need to be lean and mean and not be wasteful of the limited resources. Continuing our comparisons, let's talk about handling intermittent connectivity. Most mobile apps in this day and age are designed to operate as best they can, even when Wi-Fi and cell signals are lost. The phone app doesn't crash when the signal's lost. It just disconnects the call as it should. And most modern internet-based media players and video streaming apps are able to switch seamlessly between Wi-Fi and cell connections, and they're able to buffer up that streaming media in order to handle intermittent losses of signal. But as I mentioned earlier, Curiosity and Perseverance are actually out of communication for most of their working day. There are only a couple of 8-minute-long communication satellite flyovers throughout each Martian day. So these are the only opportunities for Curiosity and Perseverance to receive commands from Earth and to transmit data back to Earth. Curiosity and Perseverance are both designed to power down each night, just like us humans. Then in the morning, a local onboard timer turns on several heaters in order to warm up the motors and the gears and anything else that needs to be warmed up. During this warm-up period, the rover's onboard computer remains off. The designers call this dream mode. I mentioned that it was very cold on Mars. The average temperature on the surface of Mars is minus 63 Celsius or minus 81 degrees Fahrenheit. That is very cold. And that is just the average temperature. We have a few places on Earth that can get colder than that, but not many. These robots are unable to move until their gears and motors are fully warmed up. So having the onboard computer running during this warm-up period is really a waste of energy. So this dream mode design conserves quite a bit of power. When it's finally time for Curiosity and Perseverance to fully wake up, another local timer powers up their onboard computers. The first thing they do is look for the orbiting comm satellite. Once connected, they automatically send the current status of all onboard subsystems, and then they wait for the day's work plan. Once they receive the day's plan, they disconnect from the comm satellite and they start executing the plan. During the day, their plan gets interrupted by a timer every time the communication satellite is scheduled to come into view. Due to physics and due to orbital mechanics, the timing of the communication satellite is very reliable. Curiosity and Perseverance take these comm satellite opportunities to send current status to Earth along with any data that they've collected since the last comm period. So that's basically how a Mars rover handles occasional communication with Earth. Quite a bit different than your typical mobile app. Now let's continue our comparisons between a typical mobile app or business app and the onboard software for a Mars rover. What about supportability and upgradability? My apps on my phone, they upgrade themselves constantly. The developers of these apps are always adding features, they're squashing bugs, and they're making improvements, which is great. It didn't used to be this way. Has anyone in this meeting ever bought software on floppy disks? I know you're dating yourselves. I'll admit that I've done it. Before the internet, we were basically stuck with one version of software. Buggy or not, that's the software we lived with. And we lived with that version for years. Boy, have times changed. Even though Curiosity and Perseverance rovers operate 350 million miles away from home, the software loads on board are designed to be able to be upgraded. We do think that we squashed all of the bugs during ground testing, but just in case, we can remotely upload and install a new software load. But aside from the possibility of software bugs, these rover missions were actually planned with a scheduled software update. A complete software changeout was planned after they landed safely on the surface. For Curiosity, when it launched from Earth, the onboard software was specifically designed for launch and transit operations. And during the 8-month trip from Earth to Mars, the entry, descent, and landing software was still being tweaked and tested here on Earth. Also during that 8-month-long transit period, the surface navigation software was still being written. Not only was the surface software incomplete when Curiosity launched, but all of the software for transit, entry, descent, and landing, plus the surface operations, it would not all fit into the computer's memory at once. And so after landing safely on the surface and being checked out by ground controllers on Earth, they uploaded a new flight software load that focused on surface operations. This was a very slow and careful and meticulous operation, because if something went wrong with the upgrade, the mission might be over. It took the team at JPL a full 2 days to upgrade the software on one of the onboard computers, and it took them another 2 days to upgrade the backup computer. And a similar update scheme was performed on Perseverance. So the software on board a Mars rover is totally upgradable at any point in the mission, although it's not that easy nor that fun to do. So it's basically avoided except when absolutely necessary. Our final comparison topic today is programming languages. There are a lot of different programming languages available to the modern mobile app and business app developer. Does anyone here in this meeting use C# or C++ for their apps? How about Objective-C or Swift? How about Java or HTML5? I imagine there might be some folks in the meeting who use drag and drop IDEs and don't even care about programming languages. Well, the onboard apps for Curiosity and Perseverance were written mostly in C because there is a lot of heritage there and a lot of code reuse from previous rover projects. The surface navigation software, however, did use C++. This surface navigation software is the most recently developed and also the most complex of all the flight software. There was no legacy surface navigation software from the previous smaller rovers for that team to use. This surface navigation software contains modules for stereo vision, for terrain assessment, for local and global waypoint planning, for visual odometry, for wheel slip checking, and keep out zone prediction. And these are all fairly complex modules. The software development team did restrict themselves to embedded C++ constructs, though. They did not use exceptions, nor did they use templates. They didn't use IO streams, nor multiple inheritance. They limited their operator overloading to new and delete only in order to create a custom safe version of a memory allocator. And they used a dedicated memory pool, and they used placement new to guarantee no system heap corruption. For Curiosity, there are nearly 8 million lines of code on board. About 1 million lines of that were written by hand, and about 3 million lines were auto-generated from software models. The flight software development team was made up of about 40 people, and it took them about 5 years from start to finish. They first created models for much of the software. These were formal models of how the software was supposed to behave. Then they used model verification tools to guarantee that the models were correct before any code was generated. And then about 3/4 of the actual flight code was generated from those verified models. This formal process guaranteed that the generated code had certain desirable properties. For example, that it was free of race conditions, free from deadlocks, free from data corruption, and from data loss. Formal methods like this have been proven to increase the reliability and the robustness of software. So these methods are often used on safety critical software systems where there is risk of loss of life or loss of very expensive space assets in this case. The intent of the flight software development team was to create zero defect software. The team followed a number of best practices, including the Power of 10 rules for developing safety critical code. The Power of 10 rules came about after software engineers studied software-related anomalies at NASA over several decades worth of projects. They created a short list of problems that seemed to be common across almost every mission. They defined a set of 10 rules that could easily be remembered by the development community and could be mechanically verified for compliance. The Power of 10 rules are essentially a risk-based coding standard, as opposed to a style-based coding standard. They were originally published in IEEE Computer Magazine back in 2006, and you can find them on their Wikipedia page. And they've also been rolled into the official JPL coding standard, which is also publicly available on the internet. I will quickly mention the 10 rules though. Rule 1, restrict to simple control flow constructs and avoid complex ones. Avoid goto and recursion. Rule 2, give all loops a fixed upper bound to prevent runaway code. Rule 3, do not use dynamic memory allocation after initialization. Rule 4, limit functions to a single printed page. Target a maximum of 60 lines per function. Rule 5, use a minimum of 2 runtime assertions per function. Rule 6, restrict the scope of data to the smallest possible scope. Rule 7, check the return value of non-void functions and check the validity of function parameters. Rule 8, limit the use of the preprocessor to file inclusion and simple macros. Rule 9, limit pointer use to a single dereference and do not use function pointers. And Rule 10, compile with all warnings enabled and use one or more source code analyzers. All warnings must be addressed before release. Now, as part of their formal process, the flight software development team adopted tool-based compliance checks. During their development and testing, every single line of code was analyzed and scrubbed on a nightly basis using 5 different advanced static analysis tools. Each tool had different strengths and warned about different things. All the code was required to go through a detailed peer review process too. Unit tests were required to have 100% code coverage, and the team ended up with about 5 lines of test code for each and every single line of flight code. And also the team was formally trained and certified. Nobody was allowed to touch flight code without having this certification. Even managers had to undergo training and certification. So there you have it. Now you know how the typical mobile app or business app stacks up against the software on board a Mars rover. There are many similarities, but there are also many important differences. The interface between the ground controllers and a Mars rover is similar to FTPing a tarball onto a server that's 350 million miles away. Mars rover software is designed only to run on one single platform, and it must be lean and mean. Rather than occasional loss of signal, the Mars rovers encounter very occasional acquisition of signal, basically the opposite of most mobile apps. Mars rover software is designed to be upgradable, but it's so risky that it's only planned to be done once during the lifetime of a rover. And that's only because it's necessary due to onboard memory limitations. And most of the Mars rover software is written in C, with some modules written in C++, but a significant portion of the code is auto-generated from models. And a very formal development process is strictly followed to increase the reliability and the robustness of the production software. After all, Mars rover software has to work perfectly the very first time that it's used in production. I hope you found this talk both interesting and informative. Now, armed with this new information, you should be able to dominate the conversation at your next cocktail party. Now, who has some questions that they'd like to ask? Although I should warn you that even though I am a software developer for NASA, I was not actually on the team that created the software on board Curiosity and Perseverance. I do have experience writing both robotic software and ground control software at the Kennedy Space Center in Florida. My software experience focuses on monitoring and controlling pad systems and also monitoring and controlling research robots that could be used on the surface of the moon someday to support human surface missions. But I will make a valiant attempt at answering any questions that you may have.
Okay, thank you very much. That was an excellent presentation. I want to apologize for the two interruptions that we had.
Not a problem.
And I want to apologize to all attendees about those interruptions. We'll do better as far as monitoring and maybe change our settings to make sure that doesn't happen again in any of our presentations in the future. So as far as questions, you guys keep posting your questions, and we're going to start with Josh Braga. His question was, how often does the rover activate its safety systems to stop commands for any set of days commands?
I believe you're asking about the safety stop that might be activated, decided on board the rover while it's going through its daily to-do list. That happens very, very rarely, and that's because the ground team who are sending these commands to the robot, they have a lot of information. They have 3D pictures of the entire environment around the robot. And so they are careful to not put the robot into dangerous situations where that safety software would end up kicking off and halting the operation.
Okay, thank you. I'm going to go to George Zipperin. I think that's how you pronounce his name. What modeling languages was used?
I don't know. I did get most of the information for this presentation on the public internet, and I don't know. I had to be careful not to put anything that wasn't already public information into this presentation. And I'm not sure that whether NASA has published that on the public internet, that kind of development detail. I apologize, I don't know the answer.
Cameron, you had a question.
Yeah, I noticed you said that you guys did not use the exception handling feature. And so I'm wondering, did you write your own exception handling, and does the NASA process differentiate between error handling and exception handling, or is it the same thing, and is it homegrown?
Yeah, that's a good question. As far as I understand, it is homegrown, and the if an error comes up in the software, that would halt the robot's motion and halt the robot's going through its task list in the same way that if the robot encountered an obstacle that it wasn't expecting, that maybe it was told to drive in a dangerous place. So same result from two completely different types of issues. Good question.
So with traditional exception handling, you have a couple of models. You have something called the termination model and the resumption model. So do I understand your process to be a resumption, some kind of fault tolerance, so that if it is stopped, there is some kind of way to restart that same operation, or does it abandon that operation until the next set of commands?
The tricky thing about it is that the robot could potentially stay in that state for a long time, because there's only a couple opportunities each day for the robot to talk to the comm satellite and to really relay its current state of I'm in a halted state to the ground. And, you know, within an 8-minute comm link, you're not very likely to understand that the robot has stopped and have time enough to send, you know, your response, you know, your reaction sequence. And so it's probably going to be, you know, a half a day later that the team is able to upload their commands in order to get the robot either away from whatever the problem was that made it halt, or it's a worst case it's a worst case scenario if the software had a problem, right? Because you potentially might have found a bug in your software. So that's going to take days or weeks for the ground team to figure that out. They're going to run their software on their surrogate rovers. They're going to run their software in simulations and try and recreate what happened. And, you know, that could potentially take weeks before they end up deciding how to handle that. So yeah, it's a state that the robot could sit in for a very long time. Of course, the robot does have these sleep states that use less power, and you know, I suspect that there is a time period where I don't know, maybe it goes into that sleep mode, but even when it's in that sleep mode, it always knows when the comm satellite is going to go overhead and always wakes up and talks to the comm satellite.
Okay.
Julie Swango is also interested in the exception handling. Could you talk a bit about not using exceptions, maybe due to older sea-level code or concerns about minimizing testability, complexity, memory leaks?
Afraid, you know, that may be something that an internet search might give you some insight into, but I'm afraid I don't have any information there. Sorry.
Okay. Christina's question is 5 lines of tests per line of source code. That's a lot of tests. Do you happen to know if NASA uses test-driven development? Also, do you happen to know why the life expectancies of the rovers is so much lower than their actual life?
Yeah, really good questions. Yeah, a lot of safety critical NASA projects do use test-driven development. And I suspect that Curiosity and Perseverance use test-driven development, even on some, you know, much smaller, much less safety critical projects that I've worked on at Kennedy. We use test-driven development even in those smaller projects. And on the question about why is the life expectancy and the actual lifetime so much different? Why doesn't the thing, you know, roll over and die when it hits its warranty period? Well, there's not an easy answer to that, other than when the hardware is designed, and I'm a software person, so my answer is going to be a little bit hand wavy, a little bit fuzzy. But when hardware is designed, you can throw a certain amount of money at a piece of hardware. Like I'm talking about like complex hardware. Let's talk about gears. The motor is not directly attached to the wheel. The motor is attached to a gear system, and then one of the gears is attached to the wheel. That's so you can gear down and you can increase your torque and that sort of thing. And so let's talk about this gearbox. You can throw a certain amount of money at this gearbox, and you can test it to failure, and this amount of money will create a gearbox that lasts this long before it just fails, you know, cracks, locks up, whatever. You can throw more money at it and make it a little fancier, use different materials, different seals, different greases. You know, you can add complexity and robustness to this gearbox by adding more money. And when you test it to failure, it'll last a lot longer. So that's kind of the basis of my knowledge. And so every NASA project has a budget, and you can't go over that budget. And so there's some things, some components that you can spend more money on, and some components that you just have to say, I just can't. We can't build a robot that is guaranteed to live forever. And so, given their budget, they make design trades, and they decide what parts to make last, make a little tougher, and what parts to make a little bit leaner. And then they test all of these pieces to failure before they build the actual robot, and that kind of helps them almost guarantee. It's not a real guarantee. Nothing's guaranteed in life, but when they go through the certification process of every single component and every single subsystem that is put onto the final robot, they're basically certifying by testing it to failure that this part is going to last this long, and this part's going to last this long, and this many cycles. And when you add all of that up, you can estimate the warranty lifetime of your robot. And so, as I said in my presentation, the warranty life of Curiosity and Perseverance is 2 years. If something breaks on these robots before 2 years, there's a contractor that's going to be in, tail between their legs. They're going to be in serious trouble. There's something went wrong in the design process, in the certification process. So they're kind of guaranteed to last 2 years. Some of the hardware is over-designed because they were able to spend a little bit of extra money on it. They could afford to spend extra money on it. And so a lot of times our NASA missions last quite a bit longer than the warranty or the design life, and that's, to my knowledge, kind of why that happens.
I have a question, even related to what you just said. As far as quality and meeting NASA's criteria, as far as software development is so stringent, how are you using open source and GitHub for repositories? How is that being utilized in also trying to meet your standards of quality?
Good question. So I have, over my software career, I have worked on some, I haven't worked on the Mars rovers, but I worked on some firing room software at Kennedy that was considered safety critical, because if that firing room software did something unexpected, very expensive hardware out at the pad was at risk. And on launch day, humans who are inside the rocket are also at risk. And so in that sort of safety critical software project, they use a very stringent, very rigid software development process. And they, like I described in this presentation, they will use real-time operating systems that are highly deterministic, and they will use hardware that is, really, really rugged. They won't just go to Best Buy and buy a laptop or even a desktop machine for that type of project. They are going to be very, very careful and certify the software to a certain degree and the hardware too. And so they're not going to be using open source software on a safety critical project like that, unless it gets put through the ringer, that the manually, the homegrown software, that has to go through the same process. And in my career, I have worked on the other side of that spectrum, where I was working on some software for a lab robot that was not putting anybody, in harm's way. And if my software made the lab robot, let's say, smack its arm against its other arm and cause damage, that was a risk we were willing to take. the lab robot was not that expensive of a robot, that, it couldn't, take a couple, licks from its own self. So like there are a lot more NASA software projects that are of that nature. And in that world, in the research and development world where I've spent a lot of my career, we totally will go out and we will find open source software. We will buy computers from Best Buy, and we will, it's a much less rigid hardware and software development process. Sometimes we do jump through some process hoops, like unit testing and peer reviews, but a lot of times we don't. On a project like that, it's not necessary. There's no risk. Just download something from the internet and try it. If it doesn't work, no harm. We do have IT. We do have IT people that are always looking over our shoulder and slapping our wrist if we accidentally install something that is going to potentially hurt NASA's network. But most of our robots are not on the NASA network, so we try to be careful about things like that. I hope that answers your question.
Yeah, and I've got one more. I promise I won't ask any more. We kind of obviously we consider NASA robots as state of the art and the best robots that among the best that humans have been able to produce, most reliable, given the fact that they're operating on other planets, right? You described the process as the robots getting basically things to do lists. At some point, state is communicated back to ground control, and there's a committee, of folks that kind of make decisions what that next list is going to look like. How far, given that that's the current architecture, how far are we away from robots on another planet like Mars that are like more fully automated, and with less human intervention in the loop, and is able to go and generate its own things to do list, able to recover from its own faults and errors? How far are we? Is that right around the corner? Is that a decade away? It's never going to happen.
It'll happen. I have confidence. So things are evolving. As I mentioned at the beginning of my presentation, Curiosity and Perseverance are the 4th and 5th robots we have sent to Mars. So things in those 5 robots, things have evolved quite a bit. Curiosity had, a little bit of automation. It was the example in my presentation where I said, activate auto drive and then go to that waypoint over there and figure out how to get there. What's the safest way to get there? Several years later, by the time we were writing the flight software for Perseverance, we had confidence and we had experience, and we're able to add more automation to Perseverance's onboard software than we did for Curiosity. And over time, the robot drivers have gotten a lot more comfortable letting the rover get itself from point A to point B, so that they don't have to, babysit and figure out the path themselves. That's always the case with new technology. You're always a little bit timid at first to try it out, and when you first try it out, you try something that's very, very hard for the robot to fail in, and then once you see that the robot's capable, the next time you might give it a little bit more challenging task, and once it proves that it can do that, you give it more and more challenging tasks, and that's been true with the robot drivers in Curiosity and Perseverance. That said, the automation in Perseverance is fairly limited. I think we'll get there. It will be a lot easier to get there when we have a lot more robots there. And if each robot is less expensive, right? If each robot costs $30 billion, I don't know what curiosity, I don't have that off the top of my head, what they cost. So don't quote me on that. But you know, it's a lot harder to let a $30 billion robot. It's probably more like three, but anyway, it's harder to let a $3 billion robot go off on its own than a 100 million or a $3 million robot, which eventually at some point in the future, maybe it's 10 years down the road, maybe it's longer than that, we will have, you know, maybe a swarm of inexpensive rover, you know, robots doing tasks on the moon and on Mars. I think probably for the moon, we'll see a large number of robots operating on the moon in the next 5 to 10 years. And then it will take, you know, at least 10 years after that before we, you know, before Congress says, hey, moon, we're good. Let's give you all this money to go to Mars now. And so it's not, estimating a timeline is not really about estimating technology. It's more about estimating what is Congress going to allow you to do. So we'll actually be better. Now that I say that, things will happen a lot sooner than that for companies like SpaceX, where, you know, they've just got a, you know, billionaire funding them to their heart's content, and you know, they don't have the budget constraints that NASA does. So if you're asking me when NASA's going to do it, I'll give you a different answer than if you're asking me when Elon Musk and SpaceX are going to do it.
Okay. Thank you very much.
Thank you. These are really great questions.
We're actually a little over time. It's 7:13, so we're gonna go ahead and end it. And thank you so much, Kurt. The answers were spectacular. Presentation, just wonderful. It's good to see the government doing things right and things working even better than what they planned. That really gives me hope for the future, you know. So we really appreciate it. We want to thank all the attendees. Trevor, you have anything to say? Oh, and we hope that you'll come back. We have an invitation out there, so we hope you'll come back and accept that.
That's next year. That's next year.
For the fall. Yeah.
I look forward to it.
Okay, great. Thank you.
Yeah, thanks again,
Trevor,
Kurt.
you want to close out?
Yeah, I just want to echo everything Tracy said. Thanks again for coming and presenting. Thanks for everyone who attended. We will edit out those 2 instances, and we will post this video, and we will let you know once it is live. Thank you again, and have a great evening, everyone.